Okay, in this video, we're going to take a look at uncertainties, but we're going to look at the visual aspect of it, which is the way that uncertainties are expressed inside of a graph or on a graph. So I think the easiest way to do this is if we just draw a picture of a graph, and I'll draw just a couple of data points. Okay, so let's take a look at different ways that we can show the error bars. So first of all, if you think about the data point, when you record the value of a data point, it's going to be that value plus or minus some value. So that's both in the dependent variable and also in the independent variable. There will be some uncertainty. So there's really, when you think about the data, it's really not a point. Okay, it's at the very least an extended object. Because when you say, for example, that the value of the data point is, let's say 5 plus or minus 1.2, well, then you're saying that it actually could go as high as 6.2 or could go actually as low as 4.8 or 3.8. So the idea is that we want to draw a line, and that line represents essentially all of the possible values for that data point. So if I draw the upward line, this is the plus value, and here's the minus value in the dependent variable. And there's also some value for the uncertainty in the independent variable. That's typically smaller in general. I'll talk about that in just a little bit. But generally speaking, you would find that it's a little bit smaller. That's essentially what the error bars should look like. So in this case, what we're saying is that if you have to pick one point, then I would pick that data point as the value. But in reality, I know because of the uncertainty that the actual value could be anywhere that would be in between, or inside, I should say, this box. So this box represents all the possible values for that particular data point. Now, the error bar itself is actually this vertical and this horizontal line, but oftentimes it's a little difficult to see those. So instead of drawing the error bars as simply being like this, occasionally you will see error bars, actually I shouldn't even say occasionally, but quite often with a small cap on top. And that cap is just there to kind of accentuate where the edge of the error bar is. It's not really part of the error bar. It's just simply there for clarification purposes. So in this case, we have an uncertainty that's a very significant uncertainty in both the dependent variable and also the independent variable. So we've created kind of like a box. And the actual data point, we feel very confident that that data point is within this box. But I don't know for sure where inside the box because that's, again, it's within the uncertainty. So I don't know its exact value. If, on the other hand, the uncertainty in the independent variable is so small that essentially it's negligible or we can ignore it, then the actual value of the data point simply lies along this line. It takes on some value along this line. Whether we do it with the cap or not without the cap really doesn't make any difference. So the value, if you pick one, of course you would pick the average value, but what you're saying with these error bars is that it could lie anywhere along here in terms of its value for the dependent variable. So that's the way you visually represent it, and you don't put it down here. Don't put the uncertainty in the label because that doesn't really make sense. The purpose of graphs is to be visual, and so to put something like that where it's not visual, you're basically forcing the person reading the graph to have to kind of mentally figure out like, well, where are these? You know, where is the range of possible values for this data? Okay, so what can we do with the uncertainties? Well, obviously, first of all, they give you some sense of the quality of the data. You can imagine that if you saw that the error bars were very large, then that would indicate that when you were making your repeated trials that you must have gotten a pretty wide range of values. So just in a general sense, the error bars are going to tell you something about the quality of the data. We would like to see the error bars be as small as possible because that would indicate that the data was very reliable, that it was very repeatable, and therefore that we would expect that we have pretty good precision to the data. We don't know about accuracy, but as far as precision, when the data is repeatable, then we have very good precision. So I'm going to draw just a few data points here. I'm going to draw them up here. I don't want this to go to the origin. Okay, so we'll just use these 4 data points. I put a little bit of scatter to them, and I'm going to draw error bars. I'm going to use a ruler to draw the error bars, and I'm going to make the error bars 1 centimeter high. This way they'll be nice and consistent for our drawing. I am not going to draw the caps on them. I don't know. It's really just personal preference. I don't personally prefer the caps. I think they look just cleaner and looks a little bit easier to read if you don't have the caps on there. But there's certainly nothing wrong with having the caps. It's very, very popular. Okay. So we have the uncertainties for the raw data are now, or process data, have been drawn on there. But now there are things that we want to get off the graph. And the two most common things that we're going to get from the graph are going to be the y-intercept. Where does the data come down to on the y-axis? When the independent variable goes to 0, what happens to the dependent variable? Does it go to 0 or does it go to some set value? So the y-intercept is one thing we'd like to know. What is the value of the y-intercept and what are the possible range of its values based on these uncertainties? And this is where the error bars are going to allow us to be able to see that. So the other thing that we'd want to know about the graphs, of course, would be the slope. And the slope must have some uncertainty, just like all measurements and all values, all calculated values. There is some uncertainty to the final answer, and we can use the error bars to be able to figure out what that uncertainty is. So what we're basically going to do is visually draw our maximum and minimum lines. Just like we would when we use the range method for uncertainties, we're going to do the same thing here, except we have to create a line which represents the highest possible value. And first of all, before we do that, let me go ahead and draw a best fit line. One thing when you're drawing a best fit line, this is really important, so listen carefully to what I'm saying. Don't connect the first and last data points. You're really kind of ignoring the first and last data point, or try to consider them equally with the other data points, and try to find what you think is the middle value of the data point. So I would say somewhere around here. Okay, and so I have some slope, and there is some y-intercept. Okay. Now that's something where obviously we would have either Google Sheets or Microsoft Excel would calculate the value of our slope, and then they would tell us what the y-intercept is. But obviously we can do it manually also. Okay, so now we want to get the uncertainty for the slope and for the y-intercept. So what I'm going to do is the maximum value that I can, for a line that I can draw that will still fit this data, and when I say fit this data, I mean it will still hit most, if not all, of the error bars. So this is really important. You're never going to hit the data points. Okay, and it's not even really the goal to hit the data points. What we're trying to do is find the trend or the pattern that the data is showing. These data points are infinitesimally small, so in reality, you're not going to be able to get to a point where you can actually hit the data point. But it doesn't really matter because remember, the data point is just one possible value among all the other possible values that are represented by the error bars. So when a trend line works well, it's going to hit the error bars. If you miss one of the error bars or many of the error bars, then that would be indication that maybe this is not as good a fit and maybe there's some other mathematical relationship that we should test out. So in this case, this looks like the data is straight. So we're ready to go ahead and do this analysis, the maximum minimum line. I'm going to connect the bottom of the first error bar to the top of the last error bar. And that is going to give me my maximum slope. And this is going to give me my minimum y-intercept. Okay, and then the other line is going to go something like this. It will go through the first error bar at the top and through the bottom of the last error bar. That is the lowest possible line that I could draw that would still fit the data, that would still hit all or nearly all of the error bars. This is our minimum slope. And sorry, I don't know why I did that in that color. This is our maximum y-intercept. Okay, so at this point, hopefully it's pretty clear. The way we're going to find the slope uncertainty is we're just going to use the range method. So we're going to take the maximum slope minus the minimum and divide it by 2. How will we find the uncertainty for the y-intercept? Same exact process. So it's going to be max minus min divided by 2. And so by drawing the error bars, it allows us to create what are the maximum possible values for both the y-intercept and the slope, and also the minimum values. And then that allows us to use the range method to determine uncertainty. And oftentimes the goal of our research and of our investigation is to know the slope of this thing. The slope tells us something. It could tell us the speed or the acceleration, but it tells us something physically about the object. And so knowing not only its value, but also having some sense of what's the quality of this value. You know, if I told you that we measured the value of gravity and I said that it was 9.8, and so I used the slope of a velocity time graph to come up with the value of acceleration, well, you know, of course, if I say that it's 9.6, but it's plus or minus 5, well, that's not a very good uncertainty. That's a huge uncertainty. That's more than 50% of the measurement itself. So that's what it would look like if these maximum lines were really scattered, really steep and really shallow. Then I would see a very large uncertainty, and it would be represented by the fact that my maximum minimum lines are so far apart from each other. As the precision becomes better and we find that the data varies less and less within each data point, what will happen is the error bars will get smaller and smaller. And of course, the range of my uncertainty for my y-intercept and also for the slope is getting better. They're getting more precise, not necessarily more accurate. I don't know if it's the right value, but I know that it's very consistent and that it's producing a very repeatable result. And therefore, the error bars are going to start to get a little bit smaller. And the maximum minimum slope and the maximum minimum y-intercept will both get smaller and smaller, closer to their average values. Okay, so last thing we'll leave with is, oftentimes you'll notice that I didn't draw the horizontal uncertainties, and the reason for that is because oftentimes we can omit them. So the question is, when can uncertainties be ignored? So what we do for that one is, remember, you can't compare uncertainties because oftentimes they're not even measuring the same properties. So there's clearly no way that they can even be compared. But you can compare their fractional uncertainties. So that's something that's always a fair comparison. You compare the size of the absolute uncertainty to the size of the measurement, and then that's kind of a fair way of comparing them because you're comparing the uncertainty to the actual measure of the data. So in this case, when one fractional uncertainty is 1/4 or less of the other, then we can consider it insignificant. So it's not that it doesn't exist, it's there, but it's just not significant. And therefore, we can ignore it. So let me just give you a quick example of what this might look like. So I'm just use this space right here. So let's say that we're doing we made a measurement and I have distances and times, right? So what I'm trying to probably do is come up with the velocity. So I'm using the graph of distance versus time to figure out the velocity of something. And let's say, for example, that I have a delta t over t, and that's equal to 0.03. That's maybe because I have a very, very precise timing device like a ticker timer or something like that. And my first measurement is 1.40. Then that would give me a fractional uncertainty of 0.0214 or 2.1%. Okay, let's say that we have the change in distance, and that is equal to 0.5 divided by 3. Okay, so in that case, the fractional uncertainty is 0.17 or 17%. So look, 17% is way more than 4 times bigger than 2. So the uncertainty in the time is so small that it's really not having a significant impact in the overall uncertainty. If we could go back to this box, just imagine that if this uncertainty got very, very small in comparison to the size of the times down here, then what would happen is this box would begin to get very narrow, narrower and narrower, as that uncertainty becomes less and less significant. And essentially what we're saying is that you can consider it to be fairly certain that scientists would agree that if one uncertainty is 4 times bigger than the other, or saying it the other way, that the other one is that much less, then we can ignore it. And the way you would say that is that 2% is much less than 17%. You could really even write it exactly like that. And the way you would say it verbally is that 2% is much less than 17%. So therefore, we can ignore the uncertainty in the time for everything, not only for the graph, but for anything else. Any other calculations that you make with that time, you've established that the other uncertainties are so much larger that we can essentially ignore the smaller uncertainty. And anytime that you can ignore the uncertainty, you definitely want to ignore that uncertainty. Anything that'll just take the load off a little bit from what you have to do to process all of these uncertainties, you definitely want to take advantage of that whenever you can.